It's likely you're already aware that the starlight and galactic illumination that enters our field of vision today has journeyed across billions of years of cosmic space to reach us. This ancient luminescence brings forth communications from epochs predating Earth's existence, preceding our sun's birth, and even antedating the fundamental notion of biological existence itself. Today, we direct our gaze toward the celestial dome, seeking comprehension of our cosmic origins, and a singular astronomical instrument is facilitating this quest. In December 2021, humanity deployed into the cosmos the most formidable and perceptive telescope ever constructed, the James Webb Space Telescope. This extraordinary optical instrument possesses the capability to capture the most imperceptible luminous traces emanating from remote galactic systems, explosive stellar phenomena, worlds beyond our solar system, and cosmic irregularities. Its engineering was conceived to penetrate regions of space that remained beyond the reach of any previous observational device. Following its deployment, this revolutionary telescope commenced discovering phenomena that defied conventional understanding. Among these extraordinary findings were celestial bodies that initially resembled quasars, those supremely brilliant cosmic sentinels powered by the colossal black holes residing at galactic cores. However, these particular quasars exhibited distinctive characteristics. They appeared subdued in brightness and possessed extraordinary antiquity. The telescope's observations positioned them at cosmic distances exceeding 13 billion light-years from Earth. This discovery indicates we're witnessing these objects as they existed during the universe's infancy, when cosmic age measured merely 600 to 800 million years. Initially, such findings might not appear extraordinary, considering astronomers have previously identified ancient quasars, but these specimens possess unique properties. Scientists designated them with the operational nomenclature SGLQS, representing Subaru Heisei exploration of low-luminosity quasars, though for simplicity's sake, I'll reference them as C objects. Throughout our discussion, to maintain clarity and ease of understanding, this research initiative originated well before James Webb's cosmic deployment. Yet this particular telescope provided scientists with the technological capability to analyze their structural composition and spectral characteristics with extraordinary precision never before achieved. The fundamental issue lies in the fact that such celestial phenomena simply shouldn't manifest during such early cosmic periods. Our understanding confirms that quasars represent supermassive black holes engaged in matter consumption at extraordinarily rapid rates, generating energy releases that establish them as the universe's most brilliant navigational beacons. Yet, achieving such colossal proportions, encompassing millions or potentially billions of solar masses, requires extensive temporal development. Regarding C objects specifically, sufficient time periods simply didn't exist. Considering the universe's age of merely 600 million years, developing a black hole reaching 10 million solar masses would necessitate either an exceptionally massive initial seed formation, which introduces additional complexities, or growth occurring through some ultra-efficient mechanism currently beyond our comprehension. Nevertheless, this represents only a portion of the complete enigma. The second aspect that astounded research teams involves C objects' remarkable dimness despite their enormous scale and extended existence, not suggesting James Webb's observational limitations, but rather their minimal energy output according to cosmic measurement standards. This characteristic appears puzzling because conventional quasars exhibit brilliant luminosity, making them detectable across universal boundaries. In this instance, these objects are either enveloped by concentrated gas and dust formations that suppress their radiation output, or they naturally maintain inactive states. Or perhaps our observations capture them during dormant intervals between active phases, when their central black holes temporarily exhibit reduced activity levels. However, the most remarkable revelation emerged subsequently through spectral analysis. The electromagnetic radiation originating from C objects demonstrates the existence of heavy elemental components, specifically carbon, oxygen, and magnesium. These particular elements undergo formation processes within stellar interiors and experience ejection into cosmic space during stellar death events. This indicates that complete stellar generations would have required full life and death cycles to accumulate such a diverse elemental composition. Yet the universe during that epoch remained too juvenile to exhibit such chemical complexity. This situation creates a fundamental paradox. For sea objects to display their observed characteristics, we must accept either that stellar formation occurred far more rapidly than current theories suggest, or that our established models regarding stellar and galactic evolutionary processes contain fundamental errors. Both scenarios indicate potential requirements for reconsidering basic cosmological principles. This situation naturally generates the fundamental question: through what mechanisms did black holes achieving tens of millions of solar masses develop within such compressed timeframes? Perhaps their development didn't follow stellar growth patterns as standard models propose, but instead emerged directly through collapsing gas cloud formations, a process termed the direct collapse scenario. This theoretical framework suggests that specific conditions within the early universe could have enabled massive hydrogen cloud formations to bypass stellar evolutionary stages entirely, collapsing directly into black holes possessing masses ranging from tens to hundreds of thousands of solar masses. Such primordial black hole formations could have rapidly accumulated additional mass, ultimately producing sea objects. Alternative possibilities exist. Perhaps early universe conditions facilitated different accretion modes, the fundamental processes governing matter attraction. Our conventional understanding assumes gravitational forces distribute matter accumulation across billions of years, but what evidence supports identical physical laws operating during those primordial epochs? Potentially, density variations, temperature fluctuations, and gas ionization states differed significantly. These factors could have generated exotic black hole growth mechanisms. Conceivably, specific phases existed when these objects literally attracted matter at rates dozens of times faster than contemporary models permit. Even more revolutionary hypotheses have emerged. Some propose that the cosmological temporal framework itself requires comprehensive revision. Perhaps universal expansion occurred through different mechanisms than our current understanding suggests, or constituent particles exhibited alternative behavioral patterns. Certain theoretical physicists propose we're not observing quasars whatsoever, but rather something completely different: novel matter or energy manifestations, structures entirely unknown to current science. However, these concepts remain within speculative boundaries. Nonetheless, certain observations can no longer be dismissed. James Webb's discoveries extend far beyond one or two sea objects. Dozens have been identified, with likelihood suggesting significantly greater numbers exist. Extended observational periods continue revealing additional similar objects. This pattern indicates such quasars represented common phenomena. They constitute standard cosmic features rather than exceptional cases, transitioning from anomalous discoveries to established cosmic reality. We stand at the threshold of potential cosmological revolution. Should sea objects truly represent normal early universe phenomena, comprehensive revision of cosmic youth narratives becomes necessary. What mechanisms governed initial galactic formation rates? Through what processes did these systems achieve metallic enrichment? How did supermassive black hole formation occur? These same entities continue existing within modern galactic centers, including our own Milky Way galaxy. Current answers remain elusive, yet extensive data exists. This information reveals that universal birth occurred not merely faster than previous assumptions suggested, it occurred with greater complexity. Sea object observations resemble examining ancient metropolitan centers that materialized on planetary surfaces within mere decades following planetary formation. What sources provided construction materials? Which entities constructed these formations? What factors enabled such rapid expansion? Speculation remains possible, yet with appropriate investigative tools, including archaeological methodologies, numerous theoretical frameworks will emerge, ultimately yielding accurate explanations. Currently, global scientific communities focus on sea object mysteries, constructing early universe models, comparing James Webb observations with data from additional telescopes including Subaru, ALMA, and others. They develop innovative theoretical frameworks while challenging established concepts. Throughout cosmic vastness, Obvious indicators don't exist. No explanatory voices clarify observed phenomena. No galactic signage or black hole identification markers exist, regrettably. Our only resource remains light, electromagnetic radiation that traversed billions of years before reaching telescope mirror surfaces. The James Webb Space Telescope represents among the most advanced instruments ever engineered for universal exploration. Its precision capabilities astound. It can differentiate thermal emissions from galaxies so ancient and faint that their luminous output approaches disappearance thresholds. Yet Webb lacks awareness of its observations. It doesn't formulate conclusions. Human interpretation accomplishes this function. When scientific literature reports black hole discoveries with masses reaching 50 million solar masses within specific objects, these don't represent direct measurement results. We don't directly observe these black holes. Instead, we analyze surrounding gas behavioral patterns, acceleration characteristics, and emission properties at particular wavelengths. We implement mathematical modeling, dynamic equations, and accretion physics to formulate conclusions. This represents reconstruction methodology built upon numerous indirect evidence sources. This approach represents standard practice within contemporary astrophysics. Our capacity for understanding distant cosmic objects relies entirely upon interpretative processes, and these interpretations depend upon contextual frameworks, theoretical foundations, and our definitions of universal normalcy. Most significantly, we anticipate future discoveries. Scientific advancement genuinely commences when unexplainable phenomena emerge. Sea objects have become this mystery. They resemble tracks left by unknown creatures within primordial forests. We cannot identify their creators, we cannot determine their origins, yet their presence remains undeniable and real. Perhaps these discoveries will guide us toward new understanding, because every cosmic signal contains hidden questions. Through sufficiently attentive listening, we occasionally perceive answers. The James Webb Telescope was created precisely for this purpose. Not merely for observational viewing, not simply for searching, but for discovering phenomena beyond our previous imagination. These revelations demonstrate that everything represents merely the beginning.